在香港这座城市的设置。主演钱和乐。
Good morning, fellow mathematicians. Welcome back to another video. Like I said last time, when talking about Euler's reflection formula, we are going to talk about a pretty brutal integral today. And for this video, I would like to make use of one assumption, namely that we know what the answer is going to be, okay? Because I can't really bother in this very video to derive the series that we are going to end up with. So otherwise this video would take over an hour probably. Also check out PyM's video. He made a video on that too, if I remember correctly. So yeah, check that out. And you see, I'm not.
朋友是一个坚韧不拔的纪录片，在香港这座城市的设置。主演钱和乐、罗欧斯、福波斯伊。
So remember what we are going to do today is we are going to take a look at gamma of z times gamma of 1 minus z. And we already know by the previous video that this is going to evaluate to pi over the sine of pi times z. This is equivalent to pi times the cosecans of pi times z. For this, I would like to take a look at the integral definitions of the gamma function right here. So gamma function of z is nothing but the improper integral from 0 to infinity. I have derived this before. Then we are going to get t to the z minus 1 power times e to the negative tth power, integrate with respect to t. This is the first one. And now use this integral, make a change of variables, say this is s instead of t, and plug 1 minus z into here. Times the integral from 0 to infinity of, okay, you see we are going to end up with a double integral. That's already pretty hardcore. Okay, okay, s to the, okay, we are going to get rid of the 1, so just negative z power right here, e to the negative s power integrated with respect to s. Those variables are actually independent to each other, so it really doesn't quite matter. We can just bring those integrals together. So we can anti-Fubini this shit right here to make this into a double integral. At first, our outer integral is with respect to t, meaning we have an integral from 0 to infinity with respect to t, of an integral from 0 to infinity with respect to s, of t to the z minus 1 power times s to the negative z power, e to the negative t, and e to the negative s. We can bring this together as e to the negative s plus t. And this integral right here is basically a standard result that you probably find somewhere in some analytic number theory book. So I didn't come up with this, it's just something that's out there already. But I went through the calculations all by myself. So yeah, then we have ds dt. Now how can we actually integrate something like this? So that's a double integral, and I would like to make a change of variable. One obvious change of variable is to get rid of this s plus t right here. So the first thing that we are going to do is we are going to say let, for example, tau be equal to s plus t. One other thing that is not too obvious at the moment is to substitute another variable, let's say omega, as being t over s. Why does it make sense to choose t over s right here? Well, if you take a look at those two, we can rewrite them. So that's my idea here, as nothing but, okay, this is 1 over t, doesn't matter, and then we have t to the zth power over s to the zth power. So this is t over s to the zth power. That was my idea here. So this is the reason why we are going to substitute this other one. Now, we want to calculate the determinant of the Jacobian matrix, meaning the Jacobian matrix is like a correction factor inside the integral. So you have a small it's like an approximation factor. So you can have a small error, just like with differentiating in higher dimensions, and this determinant of the Jacobian is going to get rid of this error basically. So the determinant of the Jacobian matrix is nothing but the determinant of, okay, we are going to have the partial derivative of our first variable s with respect to our first new variable tau, and then the second entry is s differentiated with respect to omega, and then in the next row we are going to have the partial derivative of t with respect to tau, and then the partial derivative of t with respect to omega. This is our correction factor that we are going to have, so meaning our new double integral is some new region times some new integrand times the Jacobian matrix and then times our differentials. Okay, this is how multivariable calculus works on integrals. Meaning, in order for us to actually find out those partial derivatives, we have to solve for s and t right here respectively. And yeah, this is where it already starts. So it's quite a bit, in German I would say räudisch. In English you would say disgusting probably. It's so disgusting, disgusting. So yeah, how can we go on with this? Why not solve for t right here? So multiplying both sides by s under the condition that it's not equal to 0 at the moment. So omega times s is nothing but t. Meaning we can plug our value for t into here. Meaning tau is nothing but s plus s times omega. We can factor out the s, yeah, that's correct, to end up with s times 1 plus omega. Under the condition that 1 plus omega is not equal to 0 at the moment, we end up with s being equal to tau over 1 plus omega. Okay, this should do the trick. And then we are going to deal with t right here next. So how can we express t the best? Well, we can solve for okay, yeah, we can solve for t right here probably. Let me think for a second. I didn't really think this through. I'm terribly sorry for that. Maybe I'm going to make a little cut right here. No, we want to solve for our t, meaning we have omega times s, but what is s? S is nothing but tau minus t. Okay, meaning this is omega times tau minus t, meaning we are going to end up with omega times tau minus omega times t. It's nothing but t. We can add omega times t on both sides. It's going to get rid of this. We can factor out the t right here, leaving us with t times 1 plus omega. And now we can actually divide both sides by 1 plus omega. Okay, this does make sense. We are going to get t is nothing but omega times tau over 1 plus omega. Okay, I'm terribly sorry for this little delay in thinking. Like I said, I'm doing all of this stuff out of my head. I don't have my notes right here when I'm doing videos. If I don't know the stuff out of my head, then I'm not going to do a video. And if I fail while doing a video, then I'm doing it another day. Okay, now we have to differentiate all those s's and t's right here. Meaning, our determinant of the Jacobian is going to be the determinant of. We are going to differentiate s with respect to tau, leaving us with 1 over 1 plus omega. I hope you know how differentiation works. If you don't, then this is not a video for you right here at the moment, my boy. Then differentiating s with respect to omega, this is tau times 1 over 1 plus omega, so this is tau times 1 plus omega to the negative 1 power, meaning we are going to get negative tau over 1 plus omega squared, and then the inner derivative is 1. This should do the trick. Differentiating t with respect to tau is going to give us just omega over 1 plus omega. That's a nice variable I'm using here. And then, okay, this thing right here is just tau times omega times 1 plus omega to the negative 1 power. Let me see, that means that t differentiate with respect to omega is going to give us, okay, tau stays as it is. If we differentiate this first part, this is 1 over 1 plus omega, and then we are going to let the other stuff stay, so this is plus tau times omega, and we know what this differential is. It's negative 1 over 1 plus omega squared, meaning we can advance this thing by 1 plus omega over 1 plus omega, expand this fraction, we are going to get tau plus tau times omega minus tau minus tau times omega. This and that is going to cancel out. That's a lot of stuff. Like I said, it's disgusting. Over 1 plus omega squared. Okay, so this is our differential. Tau over 1 plus omega squared. Take a piece of paper and try it out for yourself. Maybe this is also a little outtake on my second channel. And now calculating the determinant of this thing, meaning multiplying this together and then subtracting the multiplication of this thing. Okay, this is just how a 2 by 2 determinant works. This is tau over 1 plus omega to the third power. And then multiplying this together is going to give us positive omega times tau over 1 plus omega to the third power. Oh, this was looking wrong for a second, but it's pretty Gucci, because if we add those two together, we are going to get tau plus omega times tau. We can factor out the tau to get tau times 1 plus omega. 1 plus omega and 1 plus omega is going to cancel out, leaving us with tau over 1 plus omega squared. Whew. Okay. This is how it works out. Now, what is our new integral? Now, we have a new double integral. Never mind, we're going to end up with boundaries from 0 to infinity. Then, let's see, what is t to the z minus 1th power? It's just this chunk right here. So we are going to get 1 plus omega over tau times omega. This is the 1 over t term that we have right here. And then t over s to the zth power is nothing but omega to the zth power, okay? Then we are going to get e to the negative tau. ds dt is going to change to d tau d omega d tau d omega, okay? Like I said, it's quite a hard integral, to be honest. It's a lot of handiwork we have to do here. And also, we have our Jacobian determinant, which is nothing but tau over 1 plus omega squared. Tau and tau is going to cancel out. Omega and omega to the zth power is going to be omega to the z minus 1th power. Okay? And also this and this power is going to cancel out, leaving us with a double integral from 0 to infinity. And another one from 0 to infinity. Omega to the z minus 1th power over 1 plus omega, e to the negative tau power d tau d omega. Now you can Fubini this shit once again. So this chunk right here is independent of tau. You can bring it to here, also this differential, and then you integrate e to the negative tau with respect to tau, leaving us with, on this integral, negative e to the negative tau from 0 to infinity. On infinity it's going to go to 0. Okay, negative and negative becomes positive, second part of integration, and e to the 0th power is 1. So this thing is just 1, so multiplying this integral right here over this integral by 1 by 1 is going to give us just the integral from 0 to infinity of omega to the z minus 1th power over 1 plus omega d omega. This is quite hard, even on me. So you see, I'm not a math god, I'm just a regular math student who does math for fun in his free time. This is what we have right now. We have reduced this double integral bit right here to this thing. We're not even close to being done. We have to do more work on the next blackboard. So when I first did this integral, I ended up on this point right here. And the thing is, I was standing in the bus actually, because there were no seats free. At this moment I couldn't sit. Never mind, I was just thinking about it. Well, This would be pretty easy if you would just turn this right here into a Taylor series, so geometric series, but then it struck me like lightning, well, this has been a real bra moment, where 0 to infinity is our interval. So, doesn't work out, sadly. So you can't just simply turn this into the geometric series down here. Otherwise, it would be pretty simple. You would end up with a series that you could actually evaluate quite easily. Meaning I had to do a little bit of thinking. So you see, if our interval would be from 0 to 1, we could safely turn this into a geometric series. Then I thought, well, why not just do it like with the Euler experience integral I posted a while back. Meaning, if we would introduce substitution 1 over t, for example, we would actually get new bounds from 0 to 1. So that's a trick often used in integrals, so that's nothing really special. Meaning what we do, under the condition that this integral exists, if this converges, it does for certain values of z. We can actually break this up using the area interpretation of the integral into two new areas, namely 1 from 0 to 1, omega to the z minus 1 power over 1 plus omega d omega, plus the other part from 1 to infinity. Omega to the z minus 1 power over 1 plus omega d omega. Like I said, we are going to use the same trick we did in the Euler experience integral. Meaning we are going to let omega be equal to 1 over t. If we differentiate both sides implicitly, we are going to end up with d omega being equal to negative 1 over t squared dt. Right, that's how you differentiate polynomials. Easy peasy lemon squeezy. Now we can actually plug the stuff into here. Okay? We're going to have the first integral from 0 to 1, omega to the z minus 1 power, 1 plus omega, d omega, plus. Okay, like I said, if we plug 1 into here, this is 1 over 1, so our new integral goes from 1. If we let omega approach infinity, this only works out if t goes to 0 in the limit. Okay, we are going to get 1 over t to the z minus 1 power is the same as saying we have t to the 1 minus z power. Then we have over 1 plus 1 over t, and our differential is nothing but negative 1 over t squared dt. We can distribute the negative sign into here to turn around the upper and lower bounds from 0 to 1. That's pretty good here, because then we have the same upper and lower bounds. Also, this right here is nothing but t to the first power times t to the negative z power, meaning this first power and this squared is going to cancel out, so we just have 1 over t. If we distribute this into here, we are going to get a denominator of 1 plus t. Okay, overall, that's at first this standard integral that we have right here, plus turning around the upper and lower bounds, 0 to 1. T to the negative z power over 1 plus t integrated with respect to t. Now you can just say, well, let omega be equal to t. It really doesn't quite matter. Or you say, let omega be equal to y and let t be equal to y, and then you can add stuff together. It goes over the same region, so we can just collect this. Also, we have the same denominator, so we can collect this also, leaving us with an integral from 0 to 1 of, okay, let's use t as the common variable, to the z minus 1 power. Then we are going to get plus t to the negative z power over 1 plus t integrated with respect to t. And now we are safe, my boys, because positive is nothing but negative times negative in every field, meaning 1 over this chunk is nothing but the geometric series. Oh, by God, we are getting close. We are getting really close right here. That's a hard one, and I nearly lost my chalk, but it stayed by my side. Darling, darling, stay by me. Okay, integral from 0 to 1. Then we are going to get, okay, we have this chunk right here. I'm going to leave it how it is. So t to the z minus 1 power plus t to the negative z power. Then we have our infinity boy right here, which is going to give us negative 1 to the kth power and t to the kth power, integrated with respect to t. On this interval, our geometric series converges absolutely and uniformly. We can interchange our infinite summation and this integral right here. This is allowed under this condition. Let's bring negative 1 to the kth power also to the outside, leaving us with just simple polynomials to be integrated. Okay, negative 1 to the kth power, and now we are going to get integral from 0 to 1 of, okay, collecting those terms is going to give us t to the k plus z minus 1th power plus t to the k minus zth power integrated with respect to t. We can easily integrate this polynomial. It's pretty easy, so in comparison to the rest it's just child's play. Leaving us with, okay, this is going to give us just raising the power by 1 is going to give us t to the k plus zth power over k plus z plus, okay, raising the power by 1, t to the k minus z plus 1th power over k minus z plus 1 from 0 to 1. Our index starts at 0. Doesn't really quite matter, depends on your z value, but we are going to say without any restrictions our z holds such that each and every term in here has a t, meaning on all those zeros it's just going to vanish. If we plug 1 into here, 1 to any power is just 1. So overall, we are going to end up with an infinity boy, negative 1 to the kth power, and then we are going to have 1 over k plus z power over k plus z plus 1 over k minus z plus 1. You can probably multiply stuff together, do some other stuff with this. But here at this point, we are going to call it quits. Like I said, I would like to make one assumption in this video, and this is that we actually know the answer to this thing. Because you can just simply do it like I did with the Fourier series to get our cotangent Mittag-Leffler series expansion. This thing right here is actually just a series expansion of our cosecants of pi times z. Okay, kind of times 1 over pi. So this is just something that holds. Maybe I'm going to make a whole video on deriving this thing, but it's just such a mess to derive stuff like this. So you might have seen it before in my cotangent video. It's just not rewarding at all. Yeah, you are able to rigorously find out stuff like this, but it doesn't quite matter. That's not the point of this video. We have found out what this is before, and we have calculated the value of one brutal integral, no, two brutal integrals. This double integral and then this thing right here. We have reduced stuff nicely. This is all I can offer you for today. If you want to find a different method, like I said, check out Dr. Payan's video and take a look at contour integration and the dog bone contour and the complex plane and blah blah blah. It's such an absolute mess. Shit takes forever, and yeah, never mind. We know what this is. I thank you guys for watching. If you did enjoy this video, please like and subscribe, recommend channel. If you like, I'm kind of exhausted. I'm pretty tired right now for some odd fucking reason. Never mind. Buy those t-shirts I created, support the channel on Patreon, click on those Quora questions I post from time to time, and up until the next video, have a sleepy day. See ya.